I guess I'm sharing the slides now.
Yes.
Okay, so I'll try not to be too late with my talk. So thanks a lot for inviting me to make this presentation. So I'm going to share some experience with with using Tensorflow as a compute engine for the HEP analysis, and in particular for the amplitude analysis in LHCb. So just to clarify of what kind of use case I'm covering here. So this is only one kind of usage pattern where we have a not too large data set of data, and then we are we are computing some relatively complex models on top of it. So we are fitting the complex models to this data, although relatively small. That may be kind of rather broad meaning. So in LHCb, especially after the upgrade, we are in some of the data set we're expecting like hundreds of millions events. But the important thing that they should definitely fit into the memory. So just an illustration of what kind of analysis I'm speaking about. So this is a typical amplitude analysis at LHCb, and this is a rather famous one. This is the pentaquark discovery as of 2015, I believe. So this is a rather complex feat with to a not too large data set of maybe a few tens of thousand events. This is a 6-dimensional phase space, kinematic phase space we're dealing with, and the unbinned maximum likelihood fit. And the model is expressed as a traditional helicity formalism, where we have like maybe 20 helicity amplitudes from various intermediate states entering, and well, it looks rather scary here, but in fact, what it is, it's just a combination of some trigonometric functions of various helicity angles and the dynamical terms such as Brightwigness, and those angles they are obtained from the Lorentz boosts and rotations of in the kinematic phase space. So then what we are doing with this model is, of course, you have to add the detector effects, the acceptors at the background, which is more or less easy. But then what is not so easy, and sometimes you have to do, is you have to take into account the resolutions and possibly the partial reconstruction of some of the final states, in which case you have to make the integration of convolution. And of course, this is computationally more expensive. And then you do the maximum likelihood fit, which is expressed like this. And the good point is that expressed like this is very easily vectorized. So you can basically you have a number of data points and a number of normalization points, and you can compute the same function in parallel. So this is ideally single instruction, multiple data task. And in a typical analysis, what we have to do is, so it's not a single fit, but typically it's thousands of different fits, trying to use different theory models, doing some systematic variations, doing Monte Carlo studies, and so on. So this is just to give you an idea of what kind of tasks we're doing. And of course, implementing all this mathematics is usually not an easy task. So there are a few frameworks in use at LHCb, and as well as in the other flavor physics experiments that I know about. And here I'm listing just some of them. And they are basically covering different corner cases, different kinematics, and also some of them they implement some interesting optimizations like GPUs, of course, and just-in-time compilation, code generation, and so on. However, the problem with all those frameworks is that they are unfortunately not flexible enough. And as we collect more and more data, we are trying to do something that is not foreseen in the frameworks that are on market so far. And so at some point it becomes easier to just write your own framework, and probably this is why there are so many of them. Or alternatively, you want to do something, you want to have something much more flexible, so that you could have some more or less general collection of Lego bricks, of primitives that you can use you can build the fitter yourself. But of course, what you want to do is you want to be, first of all, efficient from the computational point of view, because as you have seen, the mathematics is rather complicated. But of course, then you also have to take into account the trade-off between the number of person hours to implement your code and CPU hours to run the actual fits, because we are not doing the production, we are just doing the physics analysis once and then publish the paper and more or less forget about it. So if you look into this, so it appears that actually this kind of amplitude analysis task is very much similar to what we do in the machine learning. And so you're basically fitting complex models to large amounts of data. And of course, you need tools which would allow the convenient description of those models and to do efficiency calculations with the modern hardware without really looking deeply into this hardware. And the idea is that one can reuse those tools, which are developed by the much broader machine learning community for our needs. And this is where the Tensorflow framework comes in. So Tensorflow started in 2015, and I think basically in the year from that, we already started playing with Tensorflow for the amplitude analysis at LHCb. And at that time, it was basically the only tool that combined some nice features that are very useful for our needs. And this is, of course, the ability to compile for various architectures, compile for multi-threaded CPUs, GPUs, or even distributed clusters, even mobile platforms, although probably you won't need to run your analysis on your mobile phone. And the very useful feature appeared to be the ability to calculate the automatic derivatives, which speed up greatly the gradient descent during the optimization. So, so TensorFlow follows the so-called declarative programming paradigm. So instead of actually running calculations steps by step as you write the program, you just describe what you want to calculate, and then what it does, it works on this with this so-called graph, and possibly optimizes things, compile this for different architectures and so on. So there are several front ends for several languages, and so far we are only using Python. I think this is resulting in much more compact and readable code and faster cycle. So just a brief warning is that so most of what I'll be showing here is probably kind of outdated, because so far it was based on TensorFlow version 1, while now version 2 is something that is not completely, but it looks quite different from version 1. And the idea is that so they've introduced this eager mode, which somehow blurs the boundary between the declaration and execution. So it's easier to debug, and probably it's easier to start playing with. But in my point of view, it just became more difficult to figure out what really happens as TensorFlow deals with your model. Although there are different opinions on that, I know. So I'll speak about the migration to version 2 towards the end of my presentation. So far, what is here is based on my experience with version 1. So so basically, TensorFlow represents all the calculations in the form of the data flow graphs, where you have the nodes, which are operations, and edges, which are representing the data flow. And this is, for instance, the graph for calculating the sine wave. So the data are represented by tensors, and most of the operations are vectorized. So if you write sine of x, it will calculate element-wise sine for each element in parallel. So so this is, of course, then extremely useful for maximum likelihood fits because of the parallel nature. So the input structures, and this is where I'm outdated, is abstract structures which are assigned the value only at the execution time, and this is no longer true for version 2, which are called placeholders. And the variables which can be tunable parameters of the model, for instance, weights and biases of the neurons for machine learning, or the theory models for your physics models. So just a brief idea. Maybe I can skip most of it to save time. Just how the codes looks like in TensorFlow. So you're basically first describing the mathematics, and at this stage nothing is executed. So this is basically telling TensorFlow what you want to do with your model, and then when the actual work starts is once you create something that's called session, and you call session run. So inside session run, TensorFlow compiles the code for whatever hardware you have available, and then you feed in the input data, and as a result, you get the NumPy array of whatever you wanted to calculate. So it has its own minimization algorithms, but the problem is that they are basically, of course, designed mostly for the machine learning stuff, and probably the most critical is that they are not designed to produce a global minimum, which is, of course, crucial for the physics. But in addition, they don't give you the uncertainties. They cannot do likelihood scans and so on. Although this is a kind of a different story. So in principle, you can optimize using one optimizer and then calculate the uncertainties using something else. So that's why we basically decided to run MinWi, and this is still optimal because actually most of the time is taken while calculating the likelihood. So the fact that you're using even single-threaded MinWi doesn't really matter a lot. Right. And as I said, the very useful feature is for TensorFlow is that it can calculate the automatic gradient of your function, and in many cases this speeds up the convergence by a factor of maybe 10, depending on the number of your fit parameters. So this is extremely useful, although it goes with the price of more memory used. And then in theory, TensorFlow should be able to identify which parts of the graph needs to be recalculated and which parts could be taken from cache. Although, so I think that was the original idea, and then it never worked fully, at least between the different calls of session run. So in practice, although one could manually store some parts of the graph that do not change, and then eject this value using this feed dict, which worked much better. Okay, so then another very useful feature for us is that there is an interface with SymPy. So SymPy is a symbolic algebra system for Python, so you can consider it as a Mathematica with Python interface, although it's open source. it has some useful extensions for physics calculations in particular. So you can, or useful mathematics that we're using as well. So for instance, inside this code, we are using the implementation of Wigner-D functions or Legendre polynomials from SymPy, so that we don't have to invent the wheel once more, and instead we're just using this lambdify function of SymPy that directly produces the TensorFlow graph. Okay, so as a result, what we have is the TensorFlow analysis package that is basically just the collection of standalone primitives, the HEP-related functions like, I don't know, Bright-Wigners, rotations, Lorentz boosts, and so on, log likelihood implementation. And then there is a minu interface for minimization, and you can use root numpy or uproot to read-write multiples. So the fact that it avoids the usage of classes or whatever. So this is completely functional, pure classes, pure functions, stateless objects. So this is very easy for anyone to contribute, and actually there are a lot of people who contributed so far. So you can see the components of the library here. So the only case where we actually use objects is the so-called phase space classes, which describe the kinematic phase space which we're fitting. For instance, the two-dimensional Dulles plot, four-body decays, and so on, which provides the functions to check if your point is inside the phase space, to generate distributions and so on. And otherwise, it's just the Lego bricks, which with Lorentz vectors, kinematic helicity amplitudes. There are some elements of the covariant formalism as well, QFT, like polarization matrices, vectors, gamma matrices, and so on. So, so here I was speaking so far about this low-level library of functions for TensorFlow. There is another project that I want to advertise is the ZFit, which is more high-level library, and the idea is to have the project of for generic fitting a la RuFit, but with the TensorFlow backend, and it tries to hide the TensorFlow technicalities from the user, so that the user doesn't even need to have a lot of experience with it. And there is no root dependency, so it's using iMinuit for fitting, uproot for tuples, so it's much lighter. And there is a choice of different fitters, estimators of the uncertainties, integration techniques, and so on. Well, in principle, I mean, this is a more high-level stuff, and it could use, for instance, those primitives from TensorFlow analysis to create custom PDFs. Okay, so so now I'm going to some issues here that we've discovered during our play with TensorFlow, and the first one is that TensorFlow is of course heavy, so the distribution size, but also the loading time and so on. So it if you're doing many small fits, it impacts the performance. For instance, just even loading the TensorFlow in Python takes some time. And also the memory usage, so it can easily exceed a few gigabytes of RAM for large data sets of maybe millions of points and complicated models, especially with the analytic gradient. So analytic gradient comes with a large hop cost. So you need a high performance card if you're using GPU, like Tesla works great, but it's of course costly. And another point is that double precision is absolutely essential, and this is why also you want a high performance GPU for performance, because for gaming GPUs, the double precision is not competitive. So one strange thing I've noticed a few times is that the results are not 100% reproducible between the different GPUs and CPUs. So you can sometimes have subtle differences, probably because of the floating point implementation of at least some functions. So it can sometimes even minimize to different minima, which is a bit scary. But this needs a bit more investigation. And of course, any TensorFlow implementation is less efficient than a dedicated code developed with, for instance, CUDA. But of course, it's much more flexible, so much faster to develop. So the way how we use hardware is so because there was a question in the notebook. So basically, for code development and tests, you can basically use anything. So I'm just using my laptop, even without the GPU. For the preliminary fits to data and model building, it's very convenient to have somewhere nearby in your institute a high performance machine with GPU, which is not used by too many people. So it allows a fast try and correct cycle if you want to quickly try some model, feed your data, see what happens, maybe adjust something without waiting for batch jobs to start. But then for like production type tasks, of course, you need a batch system when you have to do the toy Monte Carlo studies and systematic variations and so on. So at CERN, we are using LX batch, which has some GPU machines, although they are quite heavily used, I think, by many. So there's a large waiting time usually. And for CNRS, we also have some clustering in Lyon. But sometimes it even makes sense to even go for CPU only because of the waiting times for GPU clusters. So this is a bottleneck sometimes. So my personal vision here of going beyond TensorFlow. So I think it's very important not to be locked in with TensorFlow because so when we started this activity, it was basically the only option, while now things are developing in terms of hardware, but also in the software. And I think it's very important to design the code in such a way that TensorFlow is just one of the computational backends of many. For what kind of other computational backends we can think of is, so PyTorch, probably not, but I'm not 100% sure. Because the mathematics is I think is not well developed for us. Then you can try to use pure NumPy. Sometimes it works nice, especially for some simple fits, because it's much lighter. And but what I think is could be ideal fit for us is there's a more recent tool which is called JAX, and this is basically the NumPy replacement with the GPU support and also automatic gradient. So this seems to be ideal because we don't need all this fancy machine learning stuff on top of it. And I think it's quite easy to reach because basically NumPy and TensorFlow interfaces are very similar and doesn't come with a huge cost. And already in one of the TensorFlow libraries, PyHF, TensorFlow based, this approach is already implemented. So there's a switchable backends between JAX, NumPy, and TensorFlow. So just one word on future developments. So it's clear that version 1, okay, so I'm finishing now, should be dropped at some point. So now we have started the activity to move towards TensorFlow version 2. The work is still very much in progress, but there is also already one analysis in LHCb that is using it. And here I'm giving the link to the GitHub repository. So this is called Amputee F. And the idea is to basically somehow identify the boundaries between the existing and planned packages. And so this package will be mostly the low-level collection of primitives related to HEP analysis, while on top of it, we are planning to build something more high level. And for instance, PWA tensor waves is interested in having Tensorflow as one of the backends. And then, of course, this could also be used by ZFit machinery to create the custom PDFs. So there is a Gitter channel now set up for communication. So we are discussing this with mostly with Stefan Pflüger and Jonas Ashley from PWA and ZFit, respectively. And here is my summary. So TensorFlow seems to be gaining popularity in high energy physics. So there are a few packages already now available that use it as a general purpose computing backend. And I think this is natural because it has some useful features